So students, now we would be discussing about magnetic field on the axis of circular current carrying loop. So magnetic field on the axis of circular current carrying loop. We already had a preliminary discussion wherein we discussed about Biot, Savart's law and related things. Now in this is you know circular current carrying loop wherein the current is I, and now we have to find there is one point on the axis and this point is P. We have to find the magnetic field at this point P. Okay, so now what we will do is, let's consider one length dl here. Now the direction of this dl, to put in Biot-Savart's law, would be in the tangential direction. Now let's connect it to this point P. This is the radius, this is the radius, and let's say this is O, which is center of this circular current carrying loop, and let's assume this distance is x. Now similarly, if I take, this is on the upper side, if I take on the lower side, same thing, the direction is somewhere here, and again this is r x o I, correct. Now as per Biot-Savart's law, as per Biot-Savart's law, what will be the direction of this magnetic field which is being generated by the current flowing here at this point? So if I apply right hand palm rule, if I apply right hand palm rule, I will get to know that this is, see, it is an inward direction, inward direction. So at this point it would be inward direction. Okay, and what would be the magnetic field as per Biot-Savart's law? It would be dB is equal to mu naught 4 pi and I dl sine theta by r square. And let me write for the direction also so that you don't forget, it is right hand palm rule which you will be using. Okay, now this we have applied, but this is not a vector form. Let's try to put the vector form also. So the vector form would be what? Mu naught 4 pi and I dl cross r by r cube. Right, now you have to remember here that dB vector is perpendicular to dl vector and also dB is perpendicular to r vector. Okay, now coming on here, now this is the direction of the magnetic field which is applied here would be in the direction, it would be something like this. Correct. this is dB and this is dB as well. Okay, now one more thing, what is the direction, what is the theta between dl, you know, what is the the direction between dl and r? See, r is this, dl is this, correct? R is this, dl is this. So what is the angle between them? So angle would be 90 degrees. So I can say dB is equal to mu naught 4 pi, you know, I dl sine 90 by r square, or I can say dB is equal to mu naught 4 pi I dl by r square. I hope it is very clear here now. Okay, now let me go a bit of from here. Now by simple trigonometry you can make out that r square is equal to r square plus x square. So r can be written as, you know, under root of r square plus x square. Okay, let's just demarcate this. Okay, now I'm trying to break this up into a more simpler form. I'm trying to break it into a simpler form. So I'm using this blue pen. If I break this into a bit of simpler form, I can say that dB is in this direction or this direction, both sides, right? Now if I draw the axis here, this would, and this angle is theta, it will be dB cos theta, this will be dB cos theta, and this will be dB sin theta, and again this will be dB sin theta. Okay, so now what I am doing here is I am using this knowledge of mine, you know, back here in the Biot-Savart's law, and then I will integrate over the entire, you know, circular current carrying loop. Before that, by simple geometry, I can write from this figure, I can write this angle is theta. So I can write sin theta is equal to r by r. Okay, now I am going back and I am writing B net is equal to integration of dB sin theta. Okay, substituting the values, I can make it mu naught 4 pi I dl by r square into r by r, which is value of sin theta. Okay, okay. Let me use this space here. Now this can be written as B is equal to mu naught 4 pi I by r cube integration of dl. Now see, dl, integration of dl, the entire stretch would be the circumference of this, and what is the circumference? It is nothing but 2 pi r. So mu naught 4 pi ir by r cube into 2 pi R, right? Okay, now what I am doing is I am putting the value of R from here. Okay, so this becomes B is equal to I think this is visible. Let me adjust the camera. Okay, here it is. Okay, now let me write it here. Now this can be, so the final result would be B is equal to mu naught I R square divided by 2 R square plus X square whole to the power 3 by 2. Okay, so this finally is the magnetic field, on the axis of circular current carrying loop. This derivation comes in your exams, so I would highly suggest that please go through it, pause the video and go through it again, so that you have a very good understanding of the same. Okay, okay, let me go to the next page. Okay, now in this sheet I will talk that a very good aspect of this which they ask in your exam, right? Now suppose this is a current carrying loop, and this is the axis. Now and the current is flowing in this direction, correct? So what we will notice here is that at this point the current would be, or the magnetic field would be this, acting in this direction, and on the right hand side also it would be acting in this direction. See, apply Biot-Savart's law and you'll get this. So if I put let's say the Biot-Savart's law, then the direction of magnetic field is right. So number one. Number two, if I make the direction of current opposite, then I will see that the magnetic field here is something like this, something like this on the left hand side, and in the right hand side also in the same direction. This is center of the circular current carrying loop. So if I have to summarize in one line, then I can say the magnetic field is in the same direction along the axis on either side of the loop. Okay guys, very good. Okay, just read it again, try to understand. I'm pausing for 1 minute so that you get sufficient time to go through it. Okay. Okay. Now, if I have to draw a diagram, or if I have to express this in terms of a graph, I can very easily express that B is equal to minus x to plus x. Let's say this is x-axis is this, y-axis is the magnetic field. Then I can say that the graph would be something like this. And okay, so if it is negative, both would be negative if one is in negative direction. So when I talk about positive and negative direction, I am going with the direction of axis. So if it is in axis is in negative direction, then it is negative negative both, or if it is positive, then it is positive on both the side. Okay, very good. So this usually comes in your CBC exams, and it's very important. So make sure that you have a good understanding of the same. Okay. Okay, so with this, I'm taking a pause in this video, and in the next lecture, I will talk about Ampere-Circuital's law.